All right, so we're still doing convergence and divergence of a series. So we're looking at a couple more tests to add to what we've done. So we've had geometric, we have partial sums, and we had nth term test for divergence. All right, so now we'll take a look at integral test and then what we call a p-series test. Integral test. I think the integral test is easy if the integral is easy. Okay, so basically, if we have an infinite sum, what we're turning it into is an improper integral. Improper because we have to deal with this piece here. And if it's determined that this improper integral converges, then the sum converges. If we determine that it diverges, then the sum diverges. So usually the integral test is one that most people kind of like, just because you're used to doing so many integrals. So let's say we have this. Sum. N over n squared plus 1.
Oh, that's one of those inverse trig function things, right?
So it would be if there was a 1 up top.
Dang it.
But that ends, no. But you're right. This does kind of look like that inverse tan. But then that's what's throwing it off right there, that other variable. If that was a 1, it would be an inverse tan. It would be. So here's what we're going to look at. 1 to infinity of x over x squared plus 1 dx. I'm just switching to x's. That's what I usually see in my integrals. Okay. Now I'm going to determine what this integral is. This would be a u substitution because I could let u be the bottom. Du would be 2x. Does that sound right to everyone? So we're going to go u x squared plus 1 du 2x dx. So we're going to have 1/2 integral 1 over u du, which would be that natural log function. So we're going to have 1/2 ln of x squared plus 1 from 1 to infinity, and that's what I've got to evaluate. I've got to see what's going on with this guy. So if I get a value here, a finite value, converges. If I don't, diverges. That's what I'm looking at. So n goes to infinity. We're going to have 1/2 ln of infinity, and really the half's not even going to matter. Okay? And infinity squared plus 1 is just infinity. Minus 1/2 ln of 2. Now that's a finite value. I mean, it's not one I know off the top of my head. I know it's a decimal, but it's still a finite value. This, however, is infinite. Everybody agree? Natural log of infinity is infinity. Take half of it, it's still infinity. Once you're there, you are there. We're ending up with infinity. So then this thing diverges, which means this sum diverges. You okay there?
I got a question. So if they converge, do they both converge to the same thing necessarily?
No,
Okay.
do not. Sum, n goes from 1 to infinity. 1 over n squared plus 1. And the reason I say they wouldn't necessarily converge to the same thing, when we say that something's converging, other than the geometric, I really don't even know what it's converging to. I just know it's converging. That geometric, I can find that sum. Integral here. 1 to infinity. 1 over x squared plus 1 dx. Now what's this one? This one is the arctan or inverse tangent because I've got that 1 up there versus an n. So it didn't show up this time. Okay. So we're going to have inverse tan or arctan of x, or x over 1, from 1 to infinity, which would be the arctan of infinity minus the arctan of 1. Now, do you remember what the arctan of infinity is?
What in pi halves?
I have. The trig functions, think of the graph. So here's what I do. There's my tangent graph. And you might not remember it perfectly, but that should look familiar. You've seen that, okay? So what angle am I at as the tangent value is going to infinity? Well, I'm approaching pi halves. We're getting the pi halves. Whereas at 1, that would be pi fourths. Tangent of pi fourths is 1. So that's telling me that converges. So this converges. Now, as far as an integral test is concerned, because we're going to have a lot of these different tests to determine convergence or divergence, I think we'd all be really comfortable doing the integral on this guy. Use substitution, not too bad. I would think probably half of us would jump at an integral test on this, and the other half be, I don't remember those as well. Okay? Maybe we remember it a little better because we were just mentioning it back here or something. But that's where I say the integral test is nice if you're really comfortable doing the integral. So for example, if I have to do parts, I'm probably not doing the integral test.
No, sir.
Unless nothing else is working for me. That's not going to be my first choice. Because that's more work. Okay? I'm lazy. I don't want to do it. Okay? If something's going to take a while, I can do something faster, I will. Okay? So it just kind of depends on what you have. Here's another one we'll look at an integral on. This also helps us review our integrals. Get an E in there. I'm going to rewrite it as an integral. X e to the negative x squared dx. And this will be our u substitution coming back. I can let u be that negative x squared. Du becomes the negative 2x. And I'm good to go from there. Okay? So let's take a look here. U is negative x squared. Du is negative 2x dx. So negative 1/2 du is x dx. Those pieces out of there. Okay. Not a bad integral to work with. So I'm going to have the integral. Oh, sorry, negative 1/2. Get that. Integral e to the u du, which would be negative 1/2 e to the negative x squared. And then I'm going to evaluate from 1 to infinity and determine if that value converges or diverges. So we're going to have negative 1/2 e to the negative infinity. Infinity squared is still infinity. Minus, which will be plus 1/2 e to the negative 1. And the halves, you should realize by now, even if you screw up the signs or something, it's really not going to affect the convergence or divergence. Something like that. We have to evaluate what these guys are. Yeah?
Wouldn't the negative x squared be positive because it's squared?
Good question. It's really like this, negative 1 times x squared.
Okay.
So remember, you're substituting for x, squaring the x value. This is that coefficient sitting out front.
Okay.
Sometimes, that's one of those things that always fools us every now and then. If you could just try to remember if it was like a negative 2, you wouldn't do it. So you got to visualize that as a negative 1 there. We know it's there. We just sometimes forget about it because it's just sitting there with a negative sign. Okay. What does e to the negative infinity approach?
0.
0, and the half's not going to matter, right? So we're going to have a half plus 1 over 2e. That converges. I don't know, without my calculator, if what 1 over 2e is, but I know it's a value. That's enough for me. It's not a divergent amount. Second test for today. P-series. The sum as n goes from 1 to infinity of 1 over n to the p. 1 over n to the p. So I'm going to have 1 over n squared, 1 over n cubed, 1 over n to the 1/2, but there's a power on that n sitting down there. Converges if p is greater than 1, diverges if p is less than or equal to 1. Now, P-series test. It's always called the P-series test. They used to not have this in there, and then they put it back in because it was just called the P-test. People got upset about that. So, series goes in. I usually kind of think back to the geometric. So for geometric, R, because geometric had the exponent too. Right? R was less than 1, converged, greater than or equal to 1, diverge. The P-series test reverses that. So if P is greater than 1, it's going to converge. Less than or equal to 1, it's going to diverge. Like that. So let's look at one like this. Sum n goes from 1 to infinity of 1 over n. This would actually diverge because the p-value is 1. Look at the power on the n. That's a 1. So here's all I would need for my proof. P equals 1, which is less than or equal to 1, diverge. A lot of times our proof is our work we're showing. Why is it converging or diverging? What test am I using? There's not a lot to the P-series, but this is explaining that I did use that. I showed what that p-value was, what that power was for that piece. You could actually, we said how some of them work with multiple ways. Look at this guy. If I were to use the integral test we were just doing, I get ln x from 1 to infinity, ln of infinity minus ln of 1, diverge. So again, multiple tests can work. This one will be one of the ones that will come back quite often. This is also called a harmonic series. 1 over n is harmonic, and a harmonic series diverges. So yeah, we did the P-series test on here. There's one solution. This is our known series that we're going to get used to seeing more and more of. This is actually an answer stating it's harmonic, referring to it. And we were asked to do the P-series here, but you even proved it by the integral test. So sometimes there's more than one way to look at it. Now the one thing to remember is that we're talking about values at infinity. So what we need to remember is things like plus 1, minus 5, times 2. They're not changing anything. Okay, if you're doing times 2, 2 times the divergence still diverges, 2 times the convergence still converges. It's not going to matter, okay, for that piece. Same with the plus 1, minus 5, or anything like that. So let's get a different look at this. Let's go 1 to infinity, n over n plus 1 to the 5/2. Now this doesn't really look like a standard P-series because it's not just 1 over n to the p, but I can make it look like that. I'm talking about an infinite number of values. Does the plus 1 really matter? No, it's not going to change anything. So what we're really looking at is n over n to the 5/2, right? Plus 1 is not going to change anything, not when we're out there at infinity. Well, this will be the same as 1 over n 3/2. Look okay? So for large values of n, which is what we're talking about all along here, I'm not going to say that this doesn't do anything, but it's not going to matter in the grand scheme of convergence or divergence. Okay, it's not going to change any of that. We're at infinity. So I can reduce to here. Now look, p is 3/2, which is greater than 1. Converges. So sometimes it's a simple exponent. I see it right away. Sometimes we got to put some things together. Now, the last time we did that was on the geometric. Sometimes we had to rearrange the geometric to see. All right, so we're just looking at something we can rearrange here. How about this one? Let's go. Sum n goes from 1 to infinity. 5n over 2 cube root n to the 5th plus n. A lot going on here, but let's think about what really matters in determining convergence and divergence. Okay? What's something up there that does not matter? 2 doesn't matter. What else? 5 doesn't matter. You can basically just take that 5/2 and slide it out in front, right?
Yes.
Everybody agree with that? It's not going to change anything as far as convergence or divergence. Okay? All right. What else isn't going to matter? Cube root will, because that's a 1/3 power. That's an exponent. So think of roots or exponents. So exponents matter. The plus n is not going to matter. That's like adding 1,000. It's just not going to change anything, right? Now, if it was times n, it would matter because it would add another one to the exponent. Does everybody agree with that? So this is a 5th degree polynomial inside this radical. If I saw this, that's a 6th degree polynomial. It does matter then. Okay. All right, so we determined this guy isn't going to affect the power. 5 and 2 definitely don't affect the power. Okay. So basically, I'm looking at n over the cube root n to the 5th, which is n over n to the 5/3. So again, that root matters because it's part of the exponent, which would be 1 over n to the 2/3. Now I can take care of that p series. P would be 2/3, which is less than or equal to 1. Diverges. Okay there? And these would be two that I'm not going to want to integrate this guy.
Are you sure?
I'm sure. Picture the x's in there. This one, if I let u be x plus 1, then I could do the reverse and make the u minus 1 equal x, and I'll take care of that. That's still going to be more work on the integral. Right? So if I can get the powers to reduce, it makes it a little bit easier. All right.